Every system at scale has a unique personality. A news website serving millions of readers is fundamentally different from a telemetry cluster tracking millions of smart meters. One is read heavy, the other is write heavy. Designing for scale means first understanding your application's profile. Read heavy systems have a read to write ratio of 100 to 1 or more. Data changes slowly but is consumed constantly. Write heavy systems invert this ratio, ingesting a massive stream of events, logs, or metrics where reads are infrequent but write performance must be guaranteed. So in a read heavy application, we protect the primary database by intercepting requests early. The architecture relies on multiple tiers of scaling, CDNs at the edge, Redis caches in memory, and a pool of read-only database replicas downstream, where database replication is the primary way to scale read throughput. A single write-only master handles mutations, while multiple read replicas scale out queries. This introduces replica lag, where reads might fetch stale data for a split second. Caching is the ultimate shield for read-heavy systems. By keeping hot data in memory with tools like Redis, we avoid expensive database queries. Common strategies like cache aside ensure that the database is only hit during cache misses. Index optimization is key for reading fast. Database indices act like book indices, allowing queries to bypass full table scans. But indices are not free. They add severe write overhead because every write must update the index tree. Write heavy systems require a complete paradigm shift. CDNs and caches are useless here. Instead of pulling data from memory, we need to ingest high throughput streams without dropping packets, shifting our focus to queue buffers and append-only write engines. To absorb massive write bursts, we place a message broker like Apache Kafka in front of the database. Kafka acts as an ingestion buffer, absorbing spikes and letting downstream consumers write to the database in organized batches. The major bottleneck in write-heavy systems is disk I/O. Traditional databases perform random disk access to keep data organized on pages. Write-heavy architectures avoid this by using append-only logs, writing sequentially to the end of the file. Let's look under the hood of storage engines. Traditional relational databases use B trees. They organize data in balanced, hierarchical pages, allowing lightning-fast O of log n lookups. However, inserting new data requires expensive page splits and random writes. Write-heavy databases like Cassandra use log-structured merge trees or LSM trees. Instead of writing directly to disk, incoming writes go to an in-memory MemTable and are appended sequentially to a commit log, ensuring microsecond write speeds. When the MemTable fills up, it is flushed to disk as an immutable SS table. Over time, many SS tables accumulate, creating read overhead. A background process called compaction continuously merges and deduplicates these tables. This creates a clear trade-off. B trees offer fast, predictable reads but slow random writes. LSM trees offer blazing fast sequential writes but reads are slower because the engine may have to search multiple SSTables on disk. Your choice of database depends directly on this profile. Read-heavy profiles thrive on PostgreSQL, MySQL, or Elasticsearch with rich indexing. Write-heavy systems require Cassandra, InfluxDB, ScyllaDB, or Dynamo. When an application requires both high-throughput writes and complex read queries, we can separate the read and write paths completely using command query responsibility segregation or CQRS. In a CQRS architecture, writes are processed by a write-optimized command database. An event bus asynchronously broadcasts updates to sync a read-optimized query database, allowing each path to scale independently. Let's look at real-world scale. An e-commerce catalog is 99% reads. It uses distributed CDNs to cache images, Redis for product details, and Elasticsearch to serve instant searches across millions of items. Conversely, an IoT sensor fleet monitoring wind turbines is 99% writes. Millions of sensors push metrics every second. The data is buffered in Kafka, ingested sequentially by Cassandra, and rarely read until automated alerts trigger. The bottlenecks are also distinct. Read-heavy systems are limited by network bandwidth, cache hit ratios, and CPU cycles spent serializing JSON. Write-heavy systems are bound by disk IOPS, memory buffers, and compaction overhead. If tuning is profile-specific, read systems require careful cache eviction policies, query optimization, and replica load balancing. If you misconfigure caching, database connections exhaust instantly under load. Right systems require tuning buffer sizes, flush thresholds, and compaction strategies. If compaction falls behind ingestion rate, disk space exhausts, and read latency increases exponentially. Ultimately, there is no single architecture that solves all scaling challenges. By matching your storage engines, indexing strategies, and caching patterns to your application's read write profile, you build durable systems at scale.